All right, good morning, everyone. I'm going to be letting some people in right before we get started here. Just give everybody about one more minute before I start the introductions. All right, I'm sure we'll have some joining here soon, but I'll go on and start. Good morning, everyone. I'm Michael Marshall. I'll introduce myself in just a second, but you are at the AP Calculus BC content review session. This is over units 10.1 through 10.7, the convergence tests. Today, it'll be presented by Mr. Bryan Passwater. He'll have handouts available at this link. And Bryan, if you can remember to get those to Aaron, that would be great. If you haven't done so already. You can reach here as his email. Just a disclaimer, this is an online review session. It's intended for a Kentucky audience. Space permitting, though, we do welcome students from other areas. We will do all we can to provide every student with an equitable opportunity to learn. During the session, we encourage participation. We know that any participant causing a disruption to the session will be removed. And as you know, AP is a registered trademark with the College Board, of which we are not affiliated. Hosting the session is Advanced Kentucky. You can follow us on Twitter at advancedkentucky.com. I'll be moderating. I'll be monitoring the chat. If you have any technical questions, you can ask me. I'm Michael Marshall. I actually work for the Access to Algebra program with Advanced Kentucky. It's a middle school focused program to prepare students for advanced mathematics in high school. However, I did teach AP Calculus A, B, and BC for over 10 years, and also I'm currently an AP reader for the AP Calculus exam. And if you needed to reach me, I have my email right here. Just some etiquette. We ask that all participants be muted. Please leave your microphones off unless asked. Please leave your video off. However, please utilize the chat. If you have any questions, again, Bryan and myself will both be monitoring that. And with that, I'm going to turn it over to Bryan. I'm going to stop sharing my screen. Thank you so much. Bryan, it's all yours.
Awesome. Well, good morning, everybody. I'm really excited to be here. I've done a few things with Advanced Kentucky over the last few years, from a lot of the teacher focused workshops, from the summer workshops and fall, and then we just finished leading the mock exam that you guys took here recently and scoring those, and it was fun to see some of your work on those for A, B, and BC exam. So I am glad to be here. This is like a 2-hour type deal, but we're going to do about 50 minutes, 55 minutes, and then right around 11 o'clock Eastern time, we're going to take a break for about 5 to 7 minutes to kind of like get refreshed and get our mind cleared for a little bit, and then we'll come back and finish it up. So I hope you get a lot out of today. Both our sessions are geared around convergence tests, and it's one of those topics on the exam that's students struggle with a little bit. Just last night, I had a kind of my own student prep study session at my school for my BC students, and we were going through some problems, and I just had cut out like all of the convergence or series questions from last 2019 exam, and I kept them on one sheet, just let them kind of work through them in small groups a little bit. And what they found out was it's one thing to know some of the tests and to understand what the tests say, but when all those questions are just kind of thrown together with other questions on the exam, the really hard part for students, and I think teachers as well, is just even sorting them out, right? Like, how do I even know or recognize what to do? If the problem said, P series, what do you do? If it said use the ratio test, we can learn those rules and we can learn those things, and we could get to a point where we could apply that without too much difficulty. But when they're mixed up, they're not giving you any instruction, it definitely gets a little bit tricky, I think, for anybody, especially if you're learning this stuff for the first time. So I'm hoping that today, at least at the end of it, you're going to feel like convergence is kind of easy. And so what we're going to focus on are going to be, what are the actual tests that are going to be most common on the exam? What should we spend our time learning about, studying, and practicing? And what kind of things that, it's in the curriculum, it's in the CED, but this is sort of like a smaller topic or idea that maybe not is the most important thing right now, right? So we're going to focus on the most important things, but also look at some strategies for how will you know what to do and when to do it. So the title of our sessions today are going to be Convergence Made Easy, ? Right? So meaning I hope at the end you feel like I've made it a little bit easier and you feel pretty good about it. So we have to have a little math meme. This is how I feel sometimes if I solve a problem when you do it, and I'm the smartest man alive, because you have to love Billy Madison. I was actually doing a problem yesterday with my students, and it wasn't a series test. We were doing some kind of problem in our prep session, and I was solving for something. I can't remember what it was. It was an AP exam, no calculator question. The student had just brought to me. They were doing it on their own. They had found it and they were confused. So I was kind of solving it for them, and it just didn't make any sense. Like, my answer was negative the 5th root of 24 was X. I was like, that just, if you're doing an AP problem with no calculator and you're working it out, solving it, and you get X is the negative 5th root of 24, you kind of think, okay, obviously I'm wrong. This can't be right. And so I was like, I don't know, this is what I got. And then they looked it up and it was right. And I was like, I am the smartest man alive. So hopefully today you will feel like that smartest man or woman alive after we talk about these ideas. There is a chat feature. And so what might be helpful for me, and Michael's going to be monitoring the chat for us, but what will be helpful for me, I think, will be, what kind of topics or questions do you guys have, right? Normally these prep sessions, we're face to face. Like, I can see you, we can talk, we can interact. And now I'm sitting here in Indiana. I live in Indiana, kind of Indianapolis. And I don't get to see that, right? Because you have your cameras off like you're supposed to, and you can't really just communicate as well. But in the chat, can you maybe share, and you can just share it with the host only if you need to, but like, what kind of things do you feel good about with series? What kind of things do you not understand? What kind of things do you want me to focus on today? Because there's enough series stuff, enough convergent stuff to go around. So I'll let you do that here, maybe, and just kind of share, how good are you at convergence? What are your big questions? What are your big unknowns? What do you think would help you today? I'm not sure if I'll even see that or not, but I know Michael will, so he'll share any responses. Meanwhile, we'll just wait for some awkward silence on streaming here. And while you're doing that, I'm gonna let Michael interrupt me if he gets some responses to kind of share, some ideas of what I should talk about. But I'm gonna kind of start kind of doing what I was going to do, and then we can adapt it as we go along. But I think with series convergence, like, we get all these tests, and of course you have to memorize, like, the conditions of these tests. You have to memorize the conclusions of the test. But if you're just strictly trying to memorize your way through things, it's really confusing sometimes to do that, right? So it gets confusing to know, like, all these things and keeping them straight. Like, sometimes it has to be less than 1 or greater than 1, or can it equal 1? Can it not equal 1? What happens in these situations? And all these ideas, right? Now, I like what Emily mentioned in the chat for students, her students, is, how do you recognize what to do? And it seems overwhelming in your first year. And this might not make you feel better, Emily, or won't make it better for you, but it might make you feel better. I was overwhelmed with my first 5 years. So as a teacher, this is a very challenging topic to understand. But so I'm hoping I can share you some strategies for the students about, what do you look for? And I think it's really important that when you see a series or convergence type question, you have a game plan. You can't just open it and just like have no plan, because they're going to always ask questions in a way that you haven't seen. They're going to ask questions in a way that may not look like your book, that may not be phrased how you learn the test or how you learn these practice problems. And so if you're going through memorization and through repetition of problems from the book, you're going to get a question here and not even realize it's the same thing. So this is, I think, the two most overarching questions that we have to think about with series. Number one, ask yourself, what does it mean for a series to converge, right? What does that even mean? We're talking about all this convergence. What does that even mean? And number two, what does it mean for a series to diverge? And I think most students understand the idea of what a convergent means, but we misunderstand diverge. And so for a series to converge, remember what we're doing. We're adding up infinitely many numbers, which to me, to this day, is still the most like amazing thing in all of calculus, that we can add up positive numbers forever. And we can keep adding to our pile. I mean, we're making a pile. We're adding things, 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 and never, ever, ever stop. And there are some times when, even though you're adding things forever, that pile will never get out of control. That pile will never get infinite. That pile will never, get out of our ability to contain it. Meaning, I could create a box, right, of a certain size, where if we kept adding forever and ever and ever, the amount in our pile would fit the box perfectly, right? It would be an exact fit for that box. It would never go over the top of it, right? It would never overflow ever. That's incredible. You could keep adding and adding forever and still have it equal a regular number, a real number. And so it's kind of mind blowing at first, but to do that, certain things have to happen to make it possible. So what does it mean for a series to diverge? Well, our first instinct means, oh, well, it means the pile gets out of control. The pile is going to be infinity, right? Well, that's an example of a series diverging, right? Divergent, if something approaches infinity or there's no limit to it, it just keeps getting bigger and bigger without any kind of bound, that's certainly divergent. But all divergent really means is it doesn't go approach a number. So if you're adding one and then subtracting one and then adding one and subtracting one and adding one and subtracting one back and forth, right? You keep adding, subtracting forever. That's not going to get out of control, right? You're not going to get infinity for your answer, but you still won't have any answer. There's no number that your pile is getting closer to. It's just getting 1, 0, 1, 0, 1, 0 back and forth. And so that would still diverge. So divergent simply means there's no single number that your pile is approaching. That's going to be the two main ideas. And so everything we do, like if I wanted to put every single test we're going to learn today or that you learned this year in a nutshell, here's the idea. Always come back to this. If I want any series to converge, two things must be true, right? There are two requirements. So every single test we learn hits these two things, every single one. Number one, that has to be true. The terms that we're adding up, right? The summation, we're adding up a bunch of stuff. The things that we're adding up have to approach 0. So if the numbers that we're adding up don't approach 0, it will automatically diverge. This is like the nth term test, right? But that's not enough, right? So this is the first requirement, is that to have any chance of convergence, the things that you're adding up have to approach 0. And use that wording, approaches 0. It doesn't mean the numbers you're adding up have to get smaller. It means they have to approach 0, because some things will keep getting smaller and smaller and smaller, but still not approach 0. And so the things we're adding up have to approach 0, but that's not quite enough. The other rule I tell my students is they have to approach 0 fast. They have to get smaller, like closer to 0, fast enough. That's the key. Literally every convergence test is that. Do the things approach 0, and are they getting there fast enough? They can't take their time to get small, okay? So my students, of course, you should have one immediate question. Like when I see this right here, the terms have to approach 0. I can understand that. That's very clear in the script, I hope. But they have to get closer to 0 fast. And to me, the follow-up question would be, well, what's fast enough? Like, how fast is it? Well, that's exactly what every convergence test is. We don't have a rule, like it has to go this fast. It's not like a speed gun or like a radar gun where we're monitoring it. It depends on what kind of problem it is, right? Is it a p-series? Does it have factorials in it? Does it have, trig or natural logs? Is it exponential? There's so many different varieties of series that, depending on what kind of series it is, will determine how fast it is. But essentially, there is this line, just sort of imaginary line, with our numbers, where it's the divider. Like anything above this is going to be divergent, anything below it is going to be convergent. And that line about where we can separate those two things, how we can test for it, is unique for each type of problem. And so when you learn the p-series test, and when you learn the geometric series test, and when you learn the alternating series test, and when you learn the ratio test, and you learn the integral test, and the limit comparison test, and the direct comparison test, every one of those tests that you learn, it's all about this. Is it approaching 0 fast enough? Like that is literally what you're trying to do. And so when you're trying to decide, or you forget, I always forget, is it less than 1 or is it more than 1? Like what's the rule here? Well, you're going to pick the rule that makes it get small fast. What makes the numbers get smaller? And if you remember that, it helps you remember which way to make your decisions on, because you can imagine what would happen if those numbers were bigger than 1 or less than 1, and what would that do to the things that you're adding up? So that's what the heart of all of our ideas are going to be today, right? Of course, we have to throw in a little bit of Mean Girls in there. The limit does not exist. I'm pretty sure that problem wasn't even right in the movie, but it's okay.
Hey, Brian.
Yep.
I've got a couple, just so you know what people are wondering. I think several people are just asking the overall, when do you know when to use what tests? So I know you're going to hit that, but if you want to keep that in mind, I think that's the big question everyone's asking.
That's great. So I can't see that in my chat. So I'm glad that I know that.
Yeah.
So all I can see is Emily Johnson's post. You must only see the ones from the students.
I just got a couple directs to me. So
Oh, a couple direct. Okay. Gotcha. Thank you so much.
mhm.
So what a great question and what a great segue. So how will you know which one to do? So I'm going to break these up into a couple things, right? Number one, there's on multiple choice, we're going to have specific multiple choice strategies, and then we're going to have some free response strategies. I tell students in my class, when you learn calculus or you learn like for the AP exam, you have to learn it two ways. Number one, you have to be able to understand it well enough that you can explain it to like a mom or your dad or a little brother or a cousin who doesn't know calculus at all, right? If I was trying to explain calculus to my mom, I can't start talking about convergence tests of divergence in the end. She would know none of that, right? She wouldn't understand any of this. But the idea behind it is so pure and so common and intuitive. It may not seem intuitive to us because all the symbols and all the weird wording we use and it looks so complicated. But this is the one advantage about math. Like the one thing that math has over all the other courses that you can take is that we don't make stuff up. We don't create it. We just discover a truth. We discover a property that's universal. And so because of that, everything has to be connected. Everything in math is like tied together and there's never any inconsistencies or fallacies or human error like we have in other courses, right? Where we try to create something and it's great and beautiful and awesome, but yet there's inconsistencies. Like, oh, we have to learn Spanish. And I learned all the AR and ER and IR verbs. And then all of a sudden you learn, oh, wait a minute, half these words are irregular. They don't follow the pattern, right? Or I go into history and I read about history, but all of a sudden I realize, oh, in this other country, they view that history a little bit different because there's perspective involved about what our take on it is, right? And science, oh, we learned this rule and then oh, wait a minute, we were wrong. We have to readjust and recalculate. And so all those things are great courses and they're important ideas, but they're too much error involved because of it's evolving. Whereas in mathematics, we're not creating it, we're just discovering it. And we're not able to have that fallacy or that illogical part of it. Now, the downside to math is because we're discovering it, some person, right, who discovers it has to decide what we're going to call it. What are we going to name it? What symbols are we going to use? And that's where we get these really complicated, convoluted things that kind of are confusing, is because we like to mess things up and make things look more complicated than they are. But at its heart, at the core of this, everything you learn this year, whether you understand it or not yet, is very simplistic in its basic ideas. If we can get to the ideas, I guarantee you'll get the idea and you'll understand it. And so I want to make sure that we can explain it to our parents, we can explain it to our siblings in that way, not in a complicated way. Because if you can deconstruct this and get rid of all the fancy words and don't use any math talk, just use ideas, that tells me you really, really, really understand it. And that strategy is perfect for multiple choice because you're not showing your work. You're saying, do you understand this? And can you identify some quick things, which is what all those questions are about. On the free response side, that's when you have to learn how to talk to a math professor. That's when you're showing your work, you're showing your writing, you're showing your notation. So not only do you have to understand it without any math talk and sort of like decode or translate this mathanese idea into basic common, English, we have to also be able to talk and write the words like the College Board wants. And so we're going to see both of those today. How can we get to the main idea to quickly find answers for multiple choice versus how do we show that on paper? And that's when things on paper like your conditions, your notation, the symbols that you use, the naming of the stuff, your conclusions, how do you show that properly? But that doesn't make any sense. It doesn't have any usefulness if first we don't understand it. So we're going to go into some non-math technical talk, right now, which you said, how will I know what to do? Well, in my own classroom, this is not like College Board or a math like officialness. So don't think like this is some actual word. Like my teacher didn't tell me that was called this. It's not. I'm making this stuff up, right? But I call these eyeball tests, right? I call them eyeball tests because I couldn't think of anything better to say. If you have a better idea, please put it in the chat. I've been calling them eyeball tests for a long time, but I tell my students eyeball tests are tests that you can just look at the problem and you should immediately, without any work at all, give me the answer whether it converges or diverges. And this is pretty much what I would say 90% of all the questions on multiple choice about convergence are. So almost every question on multiple choice, you should not or need not any work. And I'll show you what to do. Well, how are you going to tell? Well, your question of chats were perfect. It's how will I know what to do first? And so to me, the key to all of this, and I put in this bullet point, is look for the structure of the problem. All right. Don't get caught up in the details. Look for the structure. Now that's obviously like, okay, what does that even mean? It's like telling you to think outside the box. Like, I don't know what that structure means. Well, the three eyeball tests that we're going to start with, and we're going to learn two more here in a moment, but the three main ones are going to be the end term test, the P series test, and the geometric series test. Before you even get too far on any question on the AP exam, quickly just double check. Do the numbers in this problem even approach zero? Like, to me, I tell my students that when you're in algebra and you're doing like solving equation stuff and you're trying to solve problems, you do a lot of factoring and things. I tell them the first thing you should always just quickly mentally check in the back of your mind is look for a common factor. Like, before you start doing anything else, try to factor, like by foiling or unfoiling, or whatever you guys call it. Like, don't do that until you look for a common factor. Do they have anything in common? And because what happens is you get basic, equations like 4x cubed plus x squared equals 0. And my students be like, I don't know what to do with this, because they're so used to factoring having three terms in it, right? Instead of two. Or it'll be like bigger numbers. And like, I don't know how to factor this without a calculator. I'm like, well, did you look for a common factor first? They all have a 7 in them. Take a 7 out. And once you take it out, the rest of it looks a lot easier. So keep that nth term test in your mind always. Because what happens a lot of times is there'll be a very, very basic, easy to tell test that diverges. But yet we're trying to do ratio test on it. We're trying to do all this other fancier stuff. It's like, well, why would you even do all that? The numbers don't even get closer to zero. Just stop, right? It diverges. So that's always our first go-to. And then I put P series test and the geometric test together. And this is my strategy, not just for these two, but for all tests. If you want to know, how do I categorize it? How do I know what to do? This is my first step. Look for the n, right? Every series has an n in it, right? It's kind of like our variable. Look for the n of the problem. Just go find n. It's like finding where's Waldo, but it's where's n. That's the much less exciting version of it because it's obvious where it is. And then ask yourself, what role is n playing in the problem? What I mean by that is n the base of something? On a P series, every P series problem, n is the base, right? It's n to a number power, n squared, into the P, into the 1 or whatever. It's always the base. And then on geometric series, what's n? N is the exponent. Look for n. If you see a problem and n is the base only, it's going to be P series. If n is the exponent, it's going to be geometric. And then here's the best part. If there's more than one n in the problem, like multiple ones, if all of the n's are bases, it's still a P series idea. It's still P series. And if all the n's are exponents, it's going to be geometric. Now, what happens if you have n's doing more than one thing or neither of those things? That's ratio test. 90 some percent of all the questions on the exam are going to come down to that. N is a base, only bases, P series. N is an exponent, geometric. N is multiple things, as a base and an exponent, or what the heck, there's a factorial that showed up all of a sudden? What's this natural log doing all of a sudden? When that stuff happens, that's ratio test. That's it, 3 things. Base, exponent, multiple things, or something different. P series, geometric, ratio. If you can remember those 3 tests, this exam is going to be pretty easy. So we're going to see some examples of this, right? But notice the P series test says 1 over n to the P. If P is bigger than 1, it converges. And if n is less than or equal to 1, it diverges. So for a P series, you want P to be big, right? Bigger than 1. But for a geometric series, we want the R, the common ratio, to be small, to be less than 1, right? So, well, how do you know which one it is? Because the whole point is we want these numbers to get small fast, right? They have to get small, 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 really fast. Well, if you have a P series where it's 1 over n to the P, I want that exponent big because it's in the denominator, right? So if I have that exponent big, that denominator is going to get really, really big really fast. And since it's 1 over that, my numbers will get very small. Whereas a geometric problem, I'm multiplying something over and over and over again. Well, if you're multiplying over and over and over again, it always gets bigger unless what you're multiplying is less than 1, right? So multiplying a half times a half times a half is getting smaller. But if it was a 2, for example, 2 times 2 times 2 times 2, obviously is going to get very, very big. So go back to the idea. What will make this thing get small? And that's what you want in terms of the 1 or greater than 1 or less than 1. So let's try a few of these, right? And I'm going to work through some of them with us. And so I have a couple problems on Desmos here, and I'm going to share my screen so you can see it, and I'll even share the activity at the end. So that way, if you would like to try more of these in this activity, you can, and see how you do on them. So this is what I created. I have a little card sort I have for my own students, just practicing these 3 eyeball tests, with nth term, geometric, and then p-series. And so we can take a look at this, and I turned that activity, which normally you do, with in person with cards, into a Desmos activity. So these are what it looks like. And essentially, we're going to be given a series in green here, and then we're going to pair it up. We're going to match it to which one of these tests we can use, right? The p-series, nth term, and geometric, which are 3 main eyeball tests. And then we're going to come up with a conclusion in blue. So we're kind of pairing these things up with 3 parts. So here's my series, and then we're going to decide which one it categorizes into, and then what the conclusion would be. Well, obviously, this isn't a super hard series, but I want us to practice the skill, because when the problems do get more complicated, right, it's never the easy ones that you struggle with. It's when they get really complicated and like a lot going on, that's when you're like, what do I even do? Well, go back to the heart of what I said. Just find in. If it's ever asking you about a series converging or not, just look for the in immediately. It's always your first step no matter what. And then ask yourself, what role is n playing? Is it one role or is it more than one role? Here, n is the base. So n is the base. I know immediately it's got to be a p series. So I would match those 2 things up first. And I would make that decision first before I try to make a conclusion. Just recognize it's p series. Because once you categorize it, now I can think back muscle memory, like brain memory. Okay, p series, what does it do? But don't try to classify it before you just stop and say what kind of series it is. And on the response questions, I think we always write those things backwards. I think that's what causes confusion. If you're like explaining a convergence test, we have students make their decision first. It converges by a p-series test, right? Where you name the answer first and then give the reason. Well, that's what causes problems. Why don't you figure out first the test you would use and then make a decision? Don't say it converges by p-series. Say p-series and then make a choice. Because once you say p-series, now you can stop and think, okay, what do I have to think about for p-series? How will I make my conclusion? So we're going to find what it is first. And in the p-series, the whole idea is I want this bottom to get smaller, or the denominator to get bigger, but I want the fraction to get smaller. And so we need p to be bigger than 1. And p is 2 in this case, right? We have an exponent of 2, so I know it's going to converge, right? And so it sounds kind of weird in terms of English, but I can squeeze it above it. But this converges by the p-series test. There we go. So that's kind of like a quick basic example. So let's try another one. We have 1 over 3 to the n. Well, in this case, we're looking for n, right? Well, I see the n, and I ask myself, is n the base of something or is it an exponent? Well, obviously n's the base again. The exponent here is a 1. You don't see it, but it's a 1. So it definitely is a p-series. And in fact, it's a p-series. And because n is 1, or p is 1, that is going to be our divergent rule. And this has a special name. It's called the harmonic series. Whenever you have a p-series where n is 1, it's the harmonic series. It's just a special category. You can think of it kind of like when you learn mean value theorem way back and earlier in the year. You also might have learned something called Rolle's theorem, which is a special case of mean value theorem. Rolle's theorem is what happens when the slope of the secant line is equal to 0, right? You don't have to know the name Rolle's theorem for the AP exam. Mean value theorem works for all problems, but Rolle's theorem is like a special case. Well, when P is 1, it's a special case of a harmonic series and of a larger category called P series. So you could always just say this converges by P series where P is 1, or you could just say it diverges. I didn't mean to say convert. I'm going to say diverges. Sorry, it diverges harmonic. Either one of those is fine. Let's take a look at another one. So this one, I'm going to pause for a minute and just let you take a look at it. Hopefully you can see it, okay? And then think through what your idea is. hopefully you had a chance to at least think about it. And I'm thinking, first of all, if I'm looking for n, right, I notice, first of all, there's two n's in the problem, right? And this is where this isn't too complicated, but it's a little bit more complicated looking. Like, it's not something basic, at least. It's not the +4 and the -1s kind of like distract us, or other things distract us, but we always look for the n no matter what. And n is a base on both of these, right? It's a base and it's a base. So in theory, it's kind of like a p-series problem because n is only a base. But we have to keep in the back of our mind, don't forget that nth term test, right? Always double check. Like, wait a minute, what would happen with this if n got bigger and bigger and bigger as the limit as n goes to infinity, right? Well, when that happens, these terms, the things we're adding up, just become closer and closer and closer to 3/7. Like, the limit of 3n plus 4 over 7n minus 1 as n goes to infinity means I can ignore that 4 and the 1. They won't change infinities. But this just becomes 3n over 7n, and the n's are going to just, cancel, and becomes 3/7. That doesn't mean that the series becomes 3/7. That means the numbers we're adding up become 3/7. So essentially what's going to happen in the long run is we're going to take 3/7 plus 3/7 plus 3/7 plus 3/7 plus 3/7 literally forever. Well, if you add up 3/7 forever, that will hopefully obviously give you infinity. Like, you just keep adding the same number over and over again, it's going to give you infinity no matter what, because you can never ever have a boundary. No matter what number you pick, I can keep counting long enough to get past it, right? And so this fails the nth term test, right? It doesn't even have terms that approach 0. And so this would be definitely an nth term test question, and it's going to diverge in this case. So you got to be careful for that nth term test on those problems. Michael, feel free if there's like any questions or comments or anything to interrupt me at any point in time, and I'm happy
I
to
will.
do that. So
No problem. Nothing's going on in the chat right now.
good. Michael asked me before we started if I would, want him to just interrupt me or kind of wait for a pause, and I said, feel free to interrupt me anytime. But I found that teachers are always very courteous, and they don't ever want to interrupt. So I don't want to make sure I didn't just, not give him a chance. Let's look at one more of these kind of more basic questions. All right. So here we have 2 to the n over 5 to the n minus 1, a little bit more exciting. Multiple n's again. But again, your go-to move, look where the n is at, right? Where's the n in the problem? Where's the Waldo? Where's the n? Well, there's multiple n's, but both of them are exponents, right? They're both exponents. So it doesn't really matter how many n's there are. If they're only exponents in the whole problem, then you know it's going to be geometric. So this has to be geometric automatically. So I can just put that right in there. Boom, done. And now for geometric, we know the rule is, well, what's the common ratio? The common ratio is something to the n power. Well, we have a 2 to the n on top and a 5 to the n on bottom. And I know the minus 1's kind of like, what do I do with that? Well, that's not going to change anything, because ultimately I'm still multiplying by 2 over 5. As long as it's an n and an n on top and bottom, my ratio is just 2 over 5 automatically. And if you can't see that, it's like, what? How does that work? Well, you can plug some numbers in, plug in 1 for n. That minus 1 on bottom is just going to change our first number, right? That, when n is 1, the top becomes 2, but the bottom becomes just 1 because it's 5 to the 0. So our first number is just a regular old 2. It won't be a 2/5. But the next number, right, if it is 2, I get 2 squared, which is 4. And the bottom, I get 5 to the first power to get 5. And so the first number of the series is 2. And then the second term is going to be 4 over 5. Well, if I was 2 and then getting to 4 over 5, you had to multiply by 2/5 to get there, right? So even though I'm not starting at 2/5, I'm multiplying by 2/5 each time I move forward. So I know it's going to be geometric, and the R value is 2/5, 2 over 5, because there's an n on top and the bottom. And that's going to immediately tell me that this must converge because it's geometric, where P is less than 1, right? For geometric, we want the absolute value of, I don't know why I say P, R is less than 1. So those are some like basic ideas, and you're going to see problems like this on the test, right? You're going to see some different questions that are similar to that, but then you see things kind of like this, and you're like, wait a minute, that doesn't even give me the series like in notation. So we have to realize every series has an open and a closed form, meaning if they write it with the symbols, the summation sign with like ends in it, that's certainly going to be what we call closed form. And then we have this where someone has plugged in the numbers and expanded form. And when you see this, your main idea should be, well, how would I write an equation for this? Like, what would this be? right? If it was in summation form, if it was in closed form, and the numbers, first of all, are the numbers I'm adding getting closer to 0? Well, they are. 1/2, 1/3, 1/4, 1/5, 1/6. Well, they're obviously getting closer to 0, so I can't use the end term test. Now, you might recognize this as just the harmonic series automatically, which would be wonderful, but if not, it's okay. And I'm thinking, well, the top never changes. It's always 1. It's never changing. So I was trying to write an equation for this. If something's not ever changing, that's just going to be that exact number in your equation. So the summation is going to be 1 on top, but the bottom's just like getting bigger. It's counting 1, 2, 3, 4. That's just n. The first one is a 1, then a 2, then a 3, then a 4. So this is just a summation of 1 over n. When things are changing, it's going to have an n in it. That's what n is doing. So it's 1 over n. So that is a p series. It's a p series. And because n is 1, it's n to the first power, we know that diverges. Also because it's called just simply the harmonic series. So you might see some of those problems that are more expanded a little bit that cause some confusion. This one's always like a little bit of a trap for my own students. Take a moment on this one and see what you think. Same ideas, right? We're trying to figure out whether it converges or diverges using our 3 eyeball tests, p-series, and term test, and geometric. A big trap that my own students fall into is that they quickly go to converges by geometric series test. But this is why we have our sort of our protocols. Like your first step should always be find n, right? What's in, what's in, what's in? Well, there's no n in this problem. So this can't be geometric, right? There is no n. We can't call it geometric. And what we're so used to seeing is geometric problems with that that fraction involved. You're so used to seeing that, sometimes you just jump into it, right? But it's not geometric, so we can't do it. It's not a p-series either, because there's no n. So it's not geometric or p-series. What's our other option? Well, maybe it works with the n-term test. This is literally just telling us to add up 2/3 repeatedly. It's saying, what is 2/3 plus 2/3 plus 2/3 plus 2/3? Well, those numbers are not approaching 0, right? You're adding the same number over and over again. This would fail the n-term test, and so it must diverge. So, those asking yourself what n is can help you on the more simple problems, as well as help you on the more complicated ones that we might see. I'm going to do this. I'm going to jump ahead a little bit on a couple of these. I want to show you some more of there's a lot of different problems you can practice here. If you want to go back and do it, and I'll share you with the code in case you want to try them out. Okay. But here's another one, just kind of briefly. It's this 1 plus 2 minus 3 plus 4 minus something, 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 something. Right off the bat, before you even worry about it, remember the first rule, the numbers even get closer to 0 that you're adding up. Well, obviously these numbers are not getting closer to 0. So it's going to diverge by the n-term test. So always keep that in the back of our head. And then toward the end, we have this. So I'm going to put these 4 up here, and I'm just going to give you a chance. There's 5 technically. So if you count all 5 of them correctly, this is why you don't reduce your work on the AP exam one for response. As soon as you simplify your answers, you have a chance to make a mistake. So all we're doing here is categorizing these 5 green series into the piles of, does it converge or does it diverge? So we have the series 1 over n, 2 to the 2n over 3n, 4 over n squared, -1 to the n, and then 3e to the negative n. So some of these are pretty straightforward, and some of them are going to be not like complicated looking, but there's some nuances to them, right? So see if you can mentally sort those 5. And then what I would like you to do once you do them is just direct message Michael. That way no one else has to see your answers. And don't tell which one goes into what. Just kind of write how many you had converging and how many you had diverging. So like C equals 5 and D equals 0, or C equals 2 and D equals 3. There's 5 of them there. And just once you categorize them, how many do you think you have in each category? That way I at least know that you've done the problems. I want to make sure I give you enough time to do them, but not so much time that you're just waiting and wondering what the heck is going on. And if you don't know one of them, try the ones that you know first.
Right, we got about 8 participants, so you want me to tell you when I have about 5?
Yeah, 3 or 4 or 5 is good.
Okay, I'll let you know.
Perfect, thank you. This way, also, if teachers are like, did my kid even listen or pay attention? Well, I guess we could see if they answered a question or not.
Got one response.
These are, I mean, it could be, if there's one that you can't figure out or two that you're not sure of, you could just say that the ones that you got to. Like, so if you only did 3 or 4 of them that you felt good about, you can say, 2 convergent and 1 divergent are the ones that you knew. But I just want to get a feel for, when people are doing them and when they're done.
We got about 4 responses right now.
Okay, perfect. That should be fine. If you didn't get it done, it's okay. Hopefully you had a chance to do one of them. But I really do hope that uh, everybody is at least trying some of these, because I tell my students, you guys watch me do problems all the time. And when I do them, my kids will say, and I'm sure you send me with your teacher, well, when you walk through it, it looks really easy because we're kind of guiding you on how to do it. And it makes sense to you because we're telling you, oh, P series, and you kind of know what to do. But and I know the hardest part is when you see that blank paper and no one's there kind of getting you started, prompting you and thinking about stuff. And so you have to have that own moment of, how do I start the problem without someone else giving me a hint or someone else kind of leading me to that first step. And so that's why I hope everybody's trying these. So I'm to the ones that are kind of more obvious to me first. 1/n, well, n is the base again, and the exponent's 1. This is a P series, and it's the P is 1, so I know that that diverges. That's not going to get small enough fast enough. So that one's kind of more clear to me. I'm going to jump to the 4/n squared because n's also a base, so I know it's a P series, right? N's a base, P series, and I want this exponent to be bigger than 1, which it is. So this is a P series or PS2, which converges. That will get small fast enough. And then I'm going to go to this -1 to the n, which is kind of tricky. And there's 2 ways you could think about it. Number one, if you only pay attention to the n in the problem, that's fine. N is an exponent. So this is technically geometric, right? This is a geometric series. But for geometric series, whatever you're multiplying your R value, the absolute value has to be less than 1, right? And so this is -1, and the absolute value that is 1. And so this would not quite meet our requirements. We need a value here that's smaller than 1, not equal to 1 or -1. So this would diverge using geometric series. Or you might have also noticed, wait a minute, if I'm adding this up, the first term will be -1. And the next number I'm adding is just going to be 1 because -1 squared. And the next term I'm adding is -1 again, and then 1, and then -1, and then 1. And the things I'm adding up are just bouncing between 1 and -1. So since what I'm adding up is not actually getting smaller or even closer to 0, by the nth term test, it automatically diverges because the terms, the sequence inside of here does not approach 0. So either of those methods is totally fine. Just realizing what we're adding doesn't approach 0, or it is technically geometric, but n is -1 or r is -1 doesn't work. So now I'm going to go to this E problem. This one's a little bit trickier because it's not quite n, right? You want n for the exponent. And so this is a -n, not n. So you can't say that r is e because it's not. It's not e to the n. If it was e to the n, it'd be nice and easy, but it's -n. And so a negative exponent means it's 1 over, right? And so really our R value here is 1 over E. So it's 1 over E to the n power. And so in that case, your R value is 1 over E. Well, if E is like 2.7, well, obviously 1 over that number is less than 1, right? As a fraction, 1 over E is like a small decimal. So your R value here actually is smaller than 1. So this would be convergent by the geometric series test. And then the last one, I think it's a little bit trickier. I threw it in as a twist because the common easy thing is to look at the 2 and the 3, the 2/3, and say, oh, R is 2/3, converges, right? It's geometric. N as an exponent, no problem. But again, that same rule applies. We need the exponent to just be an n. We don't care if it's +1 or -1. That won't affect anything. But this is not even that. This is 2n, and technically this is 2 squared to the n power. So if I make it as like a regular n exponent, it's not 2 to the n, it's 4 to the n on top. So the top of this is actually 4 to the n because of that little 2 in front. And the bottom is 3 to the n. So they are both exponents with an n, but the top is 4, not 2, and the bottom is 3, and 4 over 3 is bigger than 1. So this would have to diverge by the uh, geometric series. So this would actually be a divergent one. There we go. Hopefully we did okay on some of those, but they're a little bit tricky, and I know they are. And those are kind of like the more, not, I want to say straightforward problems, but they were like not overly like too much stuff, right? In the problem. So if you want to later on, try some more of those in the activity. There's more of them, and I didn't show it on the screen, and maybe I will show that.
I got a question. I'm sorry.
Yeah, go ahead, jump right in.
I didn't see my chat didn't scroll down. They wanted to ask, could you also say 4/3 plus 4/3 plus 4/3 on one of the examples? Sorry, I was taking screenshots for Twitter.
No, you're fine. I'm assuming you meant the 4/3 one might have been this one right here. So if this, because this one kind of is 4/3, you can't say 4/3 plus 4/3 plus 4/3 because there's still an n there, right? And so remember, n's changing, so it's 4/3 to the n power. So it'll be 4/3 for your first number, then your second number is going to be 4/3 squared, and then 4/3 to the third power. So really what you're adding up is 4/3 plus 4/3 squared plus 4/3 cubed plus 4/3 to the fourth power. But you could write it like that if that's what the question was. So if not, let me know. I got a message that says that's what it was. One of the things in this activity, I wasn't showing it, but I'll just point this out. If you want to go back and try this later on, after each slide, I have like a built-in check. So that way it'll give you how many you got right. So on mine, I hit check my work, and it'll show me how I did. So I got 6 cards correct. And I'm like, wait a minute, that doesn't seem right. There are more than 6 cards. Oh yeah, I left one of them off. So I can bring this back here. And if you have them all correct, it should, I hope, if I coded this correctly when I made it last year, it was like, great work, you got them all correct. So if it doesn't say you got them all correct, it'll tell you how many cards were in the right place. So you can kind of go back and figure out how many you have right at least. So I'm going to put the link for that in the chat, just in case anybody wants to use it. And I might, and I don't even know if I can send it to everybody or not. So if I can't send it to everybody, I'll let Michael broadcast it all. But I did put a link in there
I see it.
in case you want to copy and paste that for later on. And I'll also put it on the screen as well. So this is it. I mean, you can go to a direct link. What I put in the chat is a direct link, but also if you just go to student.desmos.com, it'll ask you for like the code or something, and that's the code, HSTBEU. If you don't have that written down or you lose it or forget about it, my email, I think, was shared in the beginning. I'll share it again at the end of the session, and you could just email me. I'll be happy to send you the link again. But if you're a teacher, I can send you the actual activity itself. That way, if you have a Desmos account, you can just copy it to your own account and then have it for the future for your students to use as a little activity. But it comes as part of like a hand card sort that I converted this year since we were online. So a couple more, right? Those are the 3 basic ones, and things were all nice and pretty. When I gave my kids those 3 tests, they were like, okay, this is pretty easy. I can do this. And then we get to like the 2 more interesting ones. And so these are the ones where I think students have a really hard time on. You start seeing all kinds of weird stuff in the problems, right? But they're actually really easy. I really think that if you follow some of these strategies, if you've been confused on these, that if you follow the strategies I gave you and practice it, you're gonna realize, oh, this is a lot easier than the books make it seem sometimes. So we're gonna have 2 additional eyeball tests, right? And I'm learning to, I tell my students, I'm learning to speak, not like an old man. So I do a lot of TLDRs. I still don't quite know what that meant. Something about too long, didn't read, but I'm assuming that means like here's the shortened version, right? So that's me being like relevant and youthful and hip. I tell my students I'm being hip because they just roll their eyes at me because I tell a lot of dad jokes. But so we have this limit comparison test, which, by the way, is the easiest test of all time. And we have the ratio test, which, by the way, is the easiest test of all time on multiple choice. Now, on the free response questions, if you haven't like show all your work and simplify, of course it looks a little bit harder, right? But I'm going to show you like immediate tests on multiple choice. Remember, I call these eyeball tests. I said on an eyeball test, you don't have to show any work at all. You can look at the question and know the answer immediately like that. And like, well, no, we did ratio tests. It's like, out of the ratio test, this week, and The problems are like a half a page long. I mean, I don't have to show any work. How is that possible? I couldn't ever do all that in my head. Actually, you can. You just don't know it yet. So the limit comparison test and the ratio test both have one main strategy. What's the most powerful thing in the numerator, and what is the most powerful thing in the denominator? Like what's dominating the top of this problem, and what is dominating the bottom of the problem? And everything else you can get rid of, right? So I kind of have this phrase, don't sweat the small stuff. How can I ignore everything else in the problem? Easy, because it's not going to change anything, right? When you're talking about things going to infinity, we're talking about infinite items, right? Even those other things happening, they can't control whether something is going to get out of control or not, right? The most powerful thing is going to control everything. And so we're not finding the sum of the series. We're just trying to classify it. Does it even have an answer or no, right? And the most powerful thing on top and the most powerful thing on bottom are the only things ever that will determine if there's an answer. Now, the other stuff in the problem, if there is an answer, is important because that will help determine the actual answer, right? Because those are the details for the exact number. But all we're asking is, does it have an answer or not? Which always kind of baffles me. Like, you ever wonder that? Like, we're doing all these series tests, ratio tests and comparison, all these things. And we're asking the question, does it converge or diverge? Does it have an answer or not? And then you do all this work, it converges. Yes, the series adds up to something. What's that add up to? We don't care. We have no idea. We don't. We can't even figure it out. Like almost all the problems that you do, you'll never actually ask yourself, what does this add up to? It converges. What does it equal? I don't know. Who cares? The only one that we actually know the answer to, by the way, is geometric. And so if you ever see a multiple choice problem on the exam and it's asking you for the actual sum, like what is the sum of this series? Or it has a series, like equation, and it says the series summation equals, and there's numbers for choices, like what the number is, your first instinct is just like, oh, it has to be geometric because there's no other series on the exam that you could actually find the sum of. It's geometric is it, right? A over 1 minus R, if it follows the convergent rule. So that's always a tip too. If I ask you for the sum of something, it's geometric. And that will give you a hint. So don't sweat the small stuff. So they're both the same idea. Don't sweat the small stuff. And here's the difference. Limit comparison test is when you have multiple of the same thing in the problem. Like you always look for n, right? Where's n, where's n, where's n? So if there's multiple n's in the problem, but they're all the same role, they're all bases or they're all exponents, right? Then that's the limit comparison. And we're going to ignore everything but the biggest one on top and biggest one on bottom. You're comparing the same type of n's. The ratio test is when you have multiple n's in the problem, but they're not the same, meaning you might have a factorial in there or a natural log in there or an exponential and a base, like it's a combination of things, and that's the ratio test. And we know the ratio test looks kind of long and complicated on paper when you're doing like problems by hand, but on multiple choice, it's really easy because all we're going to do is this little hierarchy here. I have this little hierarchy I use for the ratio test. And the hierarchy is look for the biggest thing on top, biggest thing on bottom. It's always the same idea. And if there's multiple like types of n's in the problem, like one's a factorial, one's exponent, all you have to do is ask yourself, where is the most powerful piece? What is the most powerful part of this problem? And if the most powerful thing is in the denominator, that series will always converge. And if the most powerful thing is in the numerator, that series will diverge because if it's in the denominator, it's making those numbers get small fast. Right? Remember, is it getting small enough, fast enough? And so if the most powerful thing is in the bottom, it's going to get small enough, fast enough. If the most powerful thing is in the numerator on top, well, it's going to make that fraction just get bigger, not smaller. So that's going to not even pass the nth term test. So here's our hierarchy. You ready? We have only 3 things that you really have to know for the AP exam. And I kind of put them in order of power. And these are kind of like specific, but we'll hopefully have a understanding of this applies to general ideas. The most powerful of all the things that we will deal with in the exam is the factorial. The factorial wins, okay? There is one thing that's kind of common above the factorial. I'm going to put it in red. This is not on the AP exam. So don't like try to learn it. But the most powerful thing is n to the n power technically. And in my class, again, I'm not sure if this is official mathematical terminology. Uh, so don't write it on the exam or in any college class. But I call n to the n power the king daddy ding dong of all functions. Like n to the n power is the king that it is like the top of the chart. Like n to the n power just destroys everything on this path. Um, but it's not on the AP exam, so don't need that. What you need to know are these three. N factorial dominates 2 to the n, and 2 to the n dominates n squared. And I use 2 as an example for like the number, but the idea is it doesn't matter what the number is. Any exponential, right? 2 to the n, 5 to the n, 4 to the n, 1,000 to the n is all the same in terms of like categorizing them. And then I use n squared for that, but it wouldn't matter. It's any polynomial, meaning n to the 1,000, n to the 50, doesn't matter. We have three categories: factorials, exponentials, and bases. Where is the n? Notice if n is the base, it's kind of like a p-series problem, right? If n is the exponent, it's kind of like geometric. Hey, those are our two eyeball tests. And then a third idea, factorial, which is kind of like a ratio test idea. So this tells me that exponentials just dominate, or the geometric series will dominate a p-series, and a factorial dominates the rest. So look for the biggest thing. Wherever it is, it just crushes everything else. And then limit comparison test, what that's saying is they're not going to have multiple roles of n. Like when you have factorials or exponentials or geometric, all these things kind of mixed, that's the ratio test. But if you have multiple n's, but they're all the same, meaning they're all polynomials, like n cubed plus n minus 4 and then n to the fourth power, like they're all bases, that's the limit comparison test. So you still can ignore everything that's not the biggest thing on top and bottom, but they're going to be the same type of n's. We're going to cancel it and reduce it. So that's a lot of like, what is going on? Let me show you and practice how this looks. So here are our three quick, wow, counting is hard today on a Saturday. There's four, I even numbered them for myself. There are four series, right? So I'm going to go through these and we're going to figure out which ones of these converge and which ones of these diverge. So when I get more complicated, right, what's your go-to move? Where's in, right? What's in doing? So on number one, I realize there's a lot of n's in this problem, but every single n I see is a base. There's nothing else happening besides n being a base. So this is basically a glorified fancy p-series problem, right? Like it's a p-series problem in a way. It's disguised, right? They're going to kind of disguise it. Don't say it's a p-series on the exam because it's not actually a p-series because you're adding stuff. But this is why the limit comparison test is here. The limit comparison test says, well, this isn't technically a p-series, but it's going to be the exact same outcome. It'll either converge or diverge based on a p-series, as long as you can find the right p-series to compare it to. Well, how do we find which p-series to compare it to? Well, we take the biggest thing on the top. What's the biggest thing on top? It's n squared, right? I can ignore everything else. Don't sweat the small stuff. What's the biggest thing on the bottom? Well, you got to be a little bit careful because we have some multiplication here. So the biggest thing actually isn't the n squared. You have to imagine what the bottom truly is. You have to distribute this. So the biggest thing on the bottom is actually 2n cubed, right? And so this is what the limit comparison test does. It ignores everything else but the biggest thing on top, biggest thing on bottom. If all the n's are the same role like they are here, they're all just bases, you have to be careful that you simplify this before you make your decision. Meaning, I can cancel out these n's, at least some of them, right? And so if I reduce this a little bit, I can reduce it by an n squared, and I get 1 on the top over just 2n. So this series right here is not the same as the problem, but they have the same fate. They're going to ride or die together, right? They're ride or dies. Like they're both going to convergent land, or they're both going to divergent land. Either way, it's going to be epic, and they're going to be happy. And so here I can look at this and say, wait a minute, that's just a p series where p is 1. This is the harmonic series, right? So this diverges, and which means that this diverges. So the goal is you look for the structure. That's what I meant earlier. I said look for the structure, look for the basic idea, and then realize n's all the same. So the first step, what's n doing? And that might help you categorize it. I'm going to jump to number 3 and show you how powerful this idea of the ratio test can be. My first step, look for the n, right? What is n doing in the problem? Well, on top in the numerator, I see n here. That's a base. Makes me think about a p-series. But then all of a sudden I see n is now an exponent. Oh crap, that's like a geometric type problem, isn't it? Oh shoot, on the bottom I have another one, which is factorial. There's 3 n's and they're all playing different roles. As soon as you have n's playing different roles, you go immediately to ratio test. So pretty much like every problem on the exam, for the most part, is going to fall into either p-series, geometric, ratio. Is in a base, is in an exponent, is in, can't decide who he is, right? I feel like on question 3, this is me like from the ages of like 18 to 42, which is how old I am right now. I can't decide who I am. Like, what do I want to do with my life, right? Even now, I'm 42. I tell my wife, I don't know what I want to do when I grow up. She's like, dude, you're 42. Like, you're out of time. But I want to do lots of things, right? So N can't decide what it wants to be. Does it want to be a P series? Does it want to be geometric? Does it want to be a factorial? Who knows? But in that case, it's way easier. What's the biggest, most powerful thing in the entire problem? The factorial is, right? That wins this fight. It doesn't matter what else is the problem. If the factorial is the most powerful thing and it's on the bottom of the problem, it will automatically converge by the ratio test. This converges by the ratio test. And when you do ratio test problems by hand, like the long way, they want to see you compute that, right? But you realize now, wait a minute. You go back to all those ratio test problems. You could have done this immediately. What's the most powerful thing? Where is it? If it's on the bottom, it converges. If it's on top, it diverges. I could have had a million things in the numerator. I could have had n to the 5th times 3 to the n times n to the 1 million times 1,000 to the n. It doesn't matter how many things you have up there. If there's a factorial on the bottom, it wins. It just crushes everything else. They're not even in the same category. It just wins, it dominates. And then finally, number 4. Again, I have multiple n's, don't I? I have a n here in the exponent and an n in the base and n in the base, and there's multiple n's. That's not a big problem, but the question is, what are those n's doing, right? And 2 of them are bases. I have this n cubed and this n to the 5th, right? Those are bases. They like, oh, it's a p-series type idea. But then I have this other n on the top, which makes it sound like it's geometric. And so as long as you have multiple roles happening, they're not all the same idea, you have to go ratio test. Right? You have to go ratio test and you just ask yourself one question. What is the most powerful? Well, exponentials are always more powerful. That just dominates. There's only one in the whole problem. It's on top. And the most powerful thing is on top. This immediately diverges by the ratio test. By the way, if you're thinking right now, if you're like cursing your teacher, like, why did Mr. So-and-so, or why did Mrs. So-and-so make me do all that stupid work? Because you're going to be doing Taylor series, right? With X involved, now you have N's and X's in the problem. And we need a ratio test because with Taylor series, the question is not, does this converge or diverge? The question becomes, what are all of the numbers of X that could work and still make it converge, right? That's what you want to know, that interval or that ratio, that rate of convergence. And so we have to know how to do the long way of ratio test so we can apply it to those problems later on. But when there's just a basic series, there's no Taylor series, there's no X, there's no power series involved. That's how the ratio test works. So we're gonna take a break because I already went past 11. When we come back, we're gonna warm up with 4 AP exam problems so you can see exactly how this applies on the AP exam, and hopefully that helped a little bit. So we'll start seeing the more complicated ones after the break and seeing more AP questions on multiple choice and free response. So I hope that does help, at least so far. And now we're gonna get a lot of practice. Michael?
What time you want everybody back, Brian?
So let's do 11, is it 11:04 right now?
It is.
Let's do 11:10, do 6 minutes and we'll jump into it.
All right. See everyone at 11:10.
Awesome. We'll get started here in about, I'll give people another 30 seconds or so. So, Michael, have you guys been face to face or are you guys virtual?
In school,
Yeah.
most of the schools around here are back in person.
Did that start like at the beginning of the school year? Is that like a recent?
Uh, in Kentucky, it was March, kind of the deadline. The governor
Huh?
wanted to write back around. I can't remember the exact date, but yeah, they're back in person.
Cool. Um, yeah, we've had in Indiana at my school, we started face to face throughout the year, and everything went really well. We had to go virtual just for a little bit. Um, After from like November, Thanksgiving time, I think, until uh, like January like 5th or something like that. We had to
It was a
go.
hodgepodge across the state. Some were always in person, others started, stopped, started. But at this point, it's everyone's back.
Sure, sure. That's good. I mean, as long as everybody's healthy and safe and things are going well, I think we all, students and teachers agree, it's better to be face to face. My own students hated it when we were virtual. They didn't, it wasn't the instruction. It was and I don't know how you guys feel who are on here, but uh, my students felt like when we were virtual, um, they didn't have like that motivation. They felt like, like no, they weren't accountable, and some teachers weren't like really making them do very much. So they kind of got in these bad habits, and they're like, they realized in the moment they needed it and they enjoyed the structure of school. Like when I'm in school all day, I think school. Like I'm here, your brain thinks I'm doing schoolwork. Because when you're
Right.
home all day, because you're home and around other stuff, they're like, I just felt like I wasn't, uh, I wasn't doing school, so it was easier to be off track. So hopefully everybody's doing okay with that. So, all right, I'm trying to copy this page over to my Smart Notebook file. I realized that for some reason something was missing from my notebook. I don't know if I deleted it right before I started or what, but I think I got it figured out. So, all right, I'm going to reshare my screen, and hopefully this will pop up and it'll be working. Um, oh, it doesn't like that at all, I guess. Oh, there we go. All right, I got it. I was having some issues, but that's because I'm bad at technology. All right, so hopefully you made it back, and we're going to kind of wrap up or do a second part of this with some actual AP problems and look at a couple other things, but these are our eyeball test, right? And so this is four different like AP exam questions. And so I'm going to maybe do this. I'm going to put it on the screen, maybe one at a time. That way we can kind of zoom in on one and not get distracted by like too many questions at one time. So let's do this. Maybe I'll do two at a time here. So let's take a look at the first one. So the first one on the top here, and this is kind of a very typical AP type, I don't want to say trick, but I feel like the College Board does this a lot, where instead of just giving you one series to check, they give you like four or three, and you have to decide which of the following series converge or which of the following series diverge, and they make you do a lot of like work, um, for one problem, right? So if you have one thing wrong, guess what's going to happen? You're going to end up getting the entire problem wrong, possibly, right? So we have to really know these ideas. And this is on those multiple choice questions like this, especially. This is certainly where all of those eyeball tests and those things that I mentioned really come into play. So if you're thinking multiple choice problems, it's almost always for these given series an eyeball type test question. So let's take a look at question one. I'm going to hide question two in case I don't want anybody to just start solving it. But which of the following series converge? Well, what's our go-to strategy? Hopefully by now, I've said it enough. You're not getting sick of me saying that, but your go-to strategy is where's n, right? Look for n in the problem. That's always your first step. And so in this case, on Roman number one, we have multiple n's and they're playing different roles, right? On Roman numeral two, multiple n's, and they're still playing different roles. Like the top is factorial, the bottom is just like a power or a base of a power. And then Roman numeral three, multiple n's again. But in this case, they're all the same idea. They're all bases, right? They're all like P series type problems. And so the first two, because the multiple n's are playing different roles, that's how you know it's ratio test, right? And so if there's multiple n's playing different roles, you just ask yourself what dominates, what wins the day, what's the most powerful thing, where is it at? Well, this one, the most powerful thing is on the bottom. And so with the ratio test, wherever that most powerful thing is will determine whether your series converges or diverges. And if the most powerful thing is on bottom, it will automatically converge. Why? Because the only two rules for a series to converge, the terms must approach zero, and they must approach zero fast enough, right? They have to get close to zero fast, quickly. And on a ratio test problem, if there's n's of a different variety, uh, and there's more than one of them, I don't know why that's in almost a highlight for some reason, but there's more than one of those in the problem. If it's in the bottom, that's going to make it get small fast. So automatically converges. So I know one works. So notice, by the way, since I know one works, the answer can't be B and the answer can't be C, right? And so if you're doing like multiple choice tests and maybe you're not sure about the whole thing, find any of them that you feel comfortable about, and you can usually eliminate a couple choices just from that. Roman numeral 2, well, the most powerful thing now is still the factorial, right? The factorial is the most powerful thing you will ever see on the BC exam. You don't get to see the king daddy ding dong, the n to the n power on the BC test. But we have this n factorial on the top, and that's going to create this problem where the whole entire series is going to diverge because of that. Because if they give us a really powerful thing in the numerator, those numbers are getting astronomically huge. You're getting big, 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 and that's going to create obviously numbers that are not approaching zero at all. So that diverges. So I know 2 doesn't work. Well, that means automatically I think 3 has to be wrong too, right? And then just to confirm, to make sure we didn't make a mistake, we should probably do the last one. Oh, and we have to do it too because we have 1 only and we have 1 and 3 only. So this is going to be the make or break. On 3, there's multiple ends, but they're all the same role, right? So they're all the same type of ends. So when that happens, that's when you just figure out, okay, well, what is the top? What's the most powerful thing on top? It's just n, right? And the bottom, what's the most powerful thing? And you can't say n because this has been factored, right? So the bottom is the entire bottom. So if you had multiplied this out, that's really what the bottom is, right? The denominator is n times n plus 2 times n plus 3. Well, please don't start foiling it because I only want the most powerful thing, which is going to be what happens when you just multiply those n's together. That term would be n cubed. And then whenever that happens, this is what the limit comparison test is. Now we just reduce it first, right? You have n over n cubed, and that becomes 1 over n squared. So this is essentially that series is going to behave the exact same way as 1 over n squared in this case. And for some reason, this happened to me during the AP Live videos. My pen just stopped recognizing itself from the computer. So it won't let me write anything down right now, but we'll get that figured out. So 1 over n squared. So that would be a P series where P is 2, in which case that means that this idea here has to automatically converge. And I'm going to see if my pen will maybe register again. I don't know. It doesn't want to seem to like it very much. So it wants to give me a random pop-up menu. So I don't know if it's allowing me to do this. I'm using my mouse right now. That's how good I am with my mouse. This is high quality mouse control right there. So I think 1 and 3 converge. So it's got to be choice D, like that. All right. So you try the next one. Same idea. Which of the following series converge? And so do the same strategy we talked about. Like if there's 1 or 2 that you feel confident on, do those first, and then maybe see if you can, adjust it. I'll give you a second to think about it. All right, hopefully you had enough time. While you were doing that, I was trying to reconnect my pen, and I'm realizing it's not my Surface Pro pen that's causing the problem. Is I think Smart Notebook just is like frozen on my pen for some reason, but uh, we'll figure it out. So this first one, it kind of scares me a little bit because we haven't even talked about sign to the of n at all, right? So I'm going to kind of pause on that one. But, okay, that's weird. Let's go to what we know, right? So don't get caught up by the first one. The second one, I see only one n in the problem, and n is the exponent. So that's a good sign, right? If n is the exponent, then I know that means that it's got to be geometric, right? It's only one exponent is geometric, but I want to make sure it's going to be written as one, to the n power. So if it's a negative n power, we got to do a little bit of work with that, right? We got to adjust it a little bit, and I'm going to see if I can write like this with my mouse. It's going to look so bad. Don't judge me, but if you write this expression, it's going to be one on the top, and then over, right? E to the n power. And this is, I think, one of the trickier geometric type ideas. And so my students are really good about recognizing that that's what it is, right? There's a summation sign in front, but I'm not going to try to draw that with a mouse only. I can't even draw that like with a regular pen and paper, let alone with a mouse control. But when you see that, it's really easy to think, oh, R is E, right? It's only an E to the n power. But when you have a fraction like 1 over something, there's also a kind of implied, you don't even have it written down, but essentially that one also has an n power because one to any power is just one, right? And so I tell my students, when you see like just a number on the bottom to the n power, you have to remember the top also was to the n power. You just don't write it because it's the number one. It won't do anything. And so when you do that and they both have n's, then you start to recognize that your R value, your common ratio in this case, is not E, it's 1 over E. And that's really important because if you thought it was E, because all you see in the problem, you're going to immediately think, oh, that's bigger than 1. It has to diverge. But your R value is 1 over E. So not having an N on the top can be a little bit of like a disguised, kind of not a trick question, but one of those ones that students will get trapped on a lot. So 1 over E is less than 1. So R value is less than 1 because E is like 2 point something. So this one definitely converges, right? So we know we have at least one convergent series, number 2. So because of that, I know I can get rid of A because not 1 only, and it's not 3 only. It doesn't make any sense. And I know it's also not E, right? Because E says 1 and 3 only. Well, I just figured out that 2 converges. So it's got to be either 1 and 2 only or just 2 only. Now, we don't have to check number 3, but I'm going to, just so we can see this idea in practice, right? We have n on top and we have n squared plus n on bottom, multiple n's, but they're all bases, right? They're all base ideas. And so if they're all bases, it's a p series idea. And the top just kind of turns into just n, right? And the bottom, well, n squared plus n, I only want the most powerful thing. If you have multiple n's, what's most powerful? And then the key with the limit comparison test is you have to reduce that before you make a choice, right? And so most powerful thing on the top is n, most powerful thing on the bottom is n squared. But when you simplify that, it becomes just 1 over n. And now it's a p series where p is 1. And that's the harmonic series, which diverges. So 3 does not work. So that's kind of confirms what we thought. So now we're back to this Roman numeral number 1. What is this sign of n? Bryan didn't even mention that anywhere in his stuff, right? Well, sign of n doesn't really do anything. It's just a number, but if you think about a sign graph, what's the highest sign goes, right? The highest it goes is 1, and the lowest it goes is -1, right? So it's not ever going to get out of control. Sine is just like a small number no matter what happens. So I do have an n on the top, which is playing a weird role, like it's a trig function. And I have an n on the bottom, which is playing a base. So there's multiple n's in the problem, right? We have n on top and on bottom. So I think, okay, well, this definitely is like a ratio test idea, right? Because we have n and n. And what's the most powerful? What wins? Well, I didn't include sign in my hierarchy, right? Of like factorials, exponentials, and polynomials. Why? Because sign doesn't even get big. It can't get big. And so the most powerful thing obviously has to be this n squared. It just crushes everything else in the problem, especially with sign's like a number. So the most powerful thing is on bottom, and n squared is certainly going to be um, a powerful enough item, right? Because it's a p series or ps2 to converge. So 1 is going to converge. And you can also think of it as sine of n, absolute value. is never bigger than 1, right? Like it's always 1 or less than 1 because it can never ever get more than that. Sign can't. And so at the top is always a number that's smaller than 1 or possibly equal to 1 at the most. Then that whole series is smaller than 1 over n squared. And if 1 over n squared converges, and this is smaller, of course it's going to converge. So I think I'm going to get, in this case, 1 and 2 only. Okay, so I'm going to have you try another one. I went the wrong way in that case. So here is going to be, I'm going to bring up these next 2 and then give you a chance to try them on, get rid of these first 2 here that we just did. And then maybe these you can try. Put them both on the screen so you have a couple minutes just to think about them on your own and then try to figure them out. So I'm going to move these lines around. I have those lines in there to separate the questions, and I'm realizing now they're kind of small, especially if you're looking at a screen that's not super big, like a Chromebook or your phone or something else. So question 3 looks like this: which of the following series converge? Same idea, except for now we see them more expanded. And then question 4, which of these series converge? And that's going to be a multiple choice question. So take a minute, and if you either have the handout or you're looking at my screen, see what you think. And Michael, I don't want to interrupt what you're doing, but I don't know if you can do this or not. I might see if you could maybe screenshot the screen for a moment
Sure.
and then maybe put it on your end. Like, can you display this? Because I want to restart my smart notebook because
Yep.
I checked my pen and my pen's fine, but I think the smart notebook just froze up.
So questions 3 and 4.
Yeah, if you screenshot that screen, and that way, if I'm going to close this out and restart it, but that way I don't lose the questions on the screen.
Got it. I'm on it.
Tell me yeah, whenever you share, I'll just close this out and redo it.
Let's go to find. Let me find the. Sorry, it's being weird. It's not,
Oh, don't worry.
not counting that as a window. So.
Well, you weren't really planning on screenshotting and sharing the screen
No,
randomly.
it's fine.
You're like, I'm over here. I'm
Let
playing
me
online
embed that
poker.
into. I got to embed it into something because it doesn't count that as a window.
Gotcha, like PowerPoint or something.
Oh, yeah. Yeah. 1 second. Trying to open a document.
Oh, you're fine.
There we go. I don't know why I was doing that. Okay, slide this over into a Google Doc. I think, okay, now this should work. Good.
Oh, perfect. Thank you. I'm just going to close this out and bring it right back here.
Okay. I'm Mark.
Hello.
Mark, what are you doing in here? You're
I
a week
just
early.
I just spent a half hour bugging Converge, and I said I was gonna say hi to you before I left. 'Cause
Oh,
I've got the kids this morning, so my wife's officiating a track meet at Baylor. So, but my 5-year-old just came through. But I just want to see what you're doing because I have to do I do the next one.
yeah. So now that now that Mark's here, I'm going to put a plug in for you guys. So next weekend, Mark will be presenting series like Taylor series. So that's really important. And the order you do these in, sometimes books or teachers do it in different orders, but they're very closely related because we're learning all about convergence, right, with just basic series right now. Because the power of this, right? We always ask ourselves. I tell my students, the first question you should ask yourself is, why do we do all these convergence tests? And we never even ask the question, if it converges, what does it equal? Like, what is this? It converges to what? I don't know. Who cares, right? The reason why we don't ask that question is because the real power is power series, right? We want to know, can you express a function, like sine or cosine or anything as a power series? In which case, we do know what it converges to. We do know the answer because it literally is whatever you get if you plug in X into the equation. So this is why we don't typically, at least in beginning calc, find just what the series adds up to, except for convergence tests. And so, except for geometric series tests. But make sure you're here next week because you're going to see really the aha moment
Yeah, the end game,
of
right?
this. Yes, like why is it we're doing these things? It's because of this. So that's going to be a really important lesson, and that's honestly going to be, I think, the most like powerfully tested part of the exam. So there's certainly going to be a lot of convergence questions on the test, on multiple choice for sure. But then when all of a sudden X starts showing up, right? It's a good life lesson. When your X's start showing up, things start to get real, like, right? In life and in math exam, when X's show up, things start to get real, and we're going to see a lot more things that are free response because you're going to start seeing use FRQs. That question 6 that we see, which is so common, is going to be part of that. So,
Yeah,
all right,
I think you touched on something there that I'll say, and then I'll leave.
go.
I'll leave you be. The convergence tests do show up in multiple choice a lot. So like a lot of the convergence test stuff you're doing at this level is just to get the intuition, because you do start to look at it and just go, oh, I know that convergence.
Yep, and Mark wasn't even here for the first part, but that's what we talked about, right, guys? We said for all these problems, I call them the eyeball test. So I said
There was a
with the ratio
2012
test.
problem on there. I recognize that 8.
Yes, I said the eyeball test are you can look at it with a ratio test and just tell right away what the most powerful thing is, and so you don't need to show all the steps of ratio test because you're going to need that when you get to the FRQs, and you have to have something a little more.
Intervals, and then these guys are important at the endpoints. Right?
Exactly. Perfect. So so join Mark next week because it's going to be a really good session, and the series question is one of the most points that you're going to get on the BC topics is going to be about series and convergence. I looked at the last exam we had for multiple choice even, and I think it was 17 or 18 questions are BC only questions on the exam. And the other 27 are going to be AB questions, right? Like that's how the exam is. 60% of the problems are AB. And so 17 or 18 problems on the multiple choice are the BC only topics, right? All those extra integration techniques, logistic ideas, Euler's method, parametrics and polars, and then series and convergence. So 17 or 18 problems are just BC topics, and 8 of those, almost half of them, were series. So like 50% of the multiple choice problems of BC only topics were these ideas. So it's a big topic.
And you nailed it, almost perfect. I just pulled up the course at a guide, or the course at a glance, and it's 17 to 18% of the exam is unit 10.
Yeah,
is what they're claiming there. So
it's a big idea. So Mark will drive that home next week, and then he knows a thing or two about the test. I think you've been a reader before, right, Mark? Have you read the exams?
At this point,
No.
comparative to the other jobs, no. But yes, I've been involved in the reading since 2005. So yeah.
Mark is a longtime reader, obviously, but he's also been a question leader. So that doesn't mean anything to you as a student. But when you guys get your papers and we have the rubrics, what the answers are, the question leaders have to kind of decide, what do you do for all the things that kind of fall in the middle? How are you going to award the point or not award the point? Where do you draw those lines? What do we want to see? And so he's going to give you a lot of really good information about not just how to solve the problems, but like Make sure you show it like this. This
Keep
is
saying
good,
this.
gets points. This does not, because it's a travesty when we see a lot of students who on their paper, we can tell they know calculus, but they're just giving away points because of how they wrote their answer. So make sure you watch that. And I think you guys will be really ready for this test.
Thanks, Brad. Good seeing you.
You too, Mark. Thank you so much. Also check out Mark on the AP Live, right? He's doing the AB videos. Tony and I are doing the BC ones this last week and the next week, and then Mark and Verge are doing the AB ones on AP Live on College Board's YouTube channel or in AP Classroom. So my pin's still not working, so I don't know what we're going to do. I don't know how we're going to figure this out, but we're going to figure it out. So I want to point out, oh, you guys did that last problem, so I want to go ahead and make sure we answer that, right? So for question 3, I hope you got it right. First thing I notice is these numbers we're adding up don't even get closer to 0. 1, -1, 1, -1. That doesn't even pass the in-term test. So for certain, that test diverges. It does not converge. So you can get rid of that one right there for sure. Number 2, when you have like this, the numbers are getting smaller and closer to 0. That's a good sign, right? That's kind of the in-term test. But here, they're giving you like the general term. This is what would have been the formula if they had done this, in a formula style with the summation sign. So it's 1 over 2n minus 1, and you look for the n, n's in the bottom, and it's a p series, right? It's really 1 over 2n. It's a p series where p is 1. This is a weirder version of the harmonic series. It's basically harmonic, and that diverges also. So 1 and 2 certainly diverge. And then the third one, of course, notice the general term, n is the exponent, right? We have our n as the power, and when n is the power, it's geometric. So all we have to decide is what is r in those cases, right? And then this is another one of those ones where you have to be a little bit careful because if there's a 1 on top, right, your r value is actually 1/3 in this case. It's not 3, it's 1/3. Because if 3 is in the bottom, it's 3 to the n, which is 1/3 to the n power technically. So r is less than 1. So Roman numeral 3 does converge, and that's our answer, C. And then question 4, which is the following series converge? Well, all 5 choices here have lots of different n's involved, right? But every n in every one of these is the base, right? These are all just fancy p series. And if this happened to be free response, by the way, if this is like an FRQ, and you're trying to explain your answer, how do you know it converges? You would just simply, we're kind of right next to the side, limit comparison to the P series. So this idea of ignoring all the other little stuff, that don't sweat the small stuff ideas for limit comparison test, the way that you would explain that on the exam on an free response is just limit comparison to whatever it turned into, right? So you kind of add that LCT even, like LCT, limit comparison test, to P series, or to 1 over n, or 1 over n squared. And so here, the biggest thing on top is n, biggest thing on bottom is n. But when I reduce those, they just cancel, don't they? And really, I'm using my mouse here. That's actually not bad. The summation of just a number 3, right? Because the n's cancel, I have a 3. Well, that's certainly, the terms don't approach 0, right? This fails the nth term test because the numbers themselves are just going to become 3. 3 plus 3 plus 3 plus 3 is going to be infinity. On B, it does reduce to 3 over n, which is a p series, but n is 1 in that case. And in that case, it's not big enough, right? We need a bigger p value than 1 to make the series converge. So that one diverges because it basically is a harmonic series. The next one, the biggest thing on top is this, this 3n, and the biggest thing on bottom is this n squared, right? So I can ignore this. We want the biggest thing on top and bottom, and that reduces to 3 over n also. Well, 3 over n is what we just did. That diverges by the p-series test. And then another one, it's the same problem, just like dressed different ways, right? The biggest thing on top is 3n squared, biggest thing on bottom is n cubed. And if you simplify all of that, you just get 3 over n again, right? Because the n squared and the n cubed reduce to just 1 over n. And so this is another p-series problem that p is 1, diverges, and I'm going to hope, let's hope that E works. Otherwise, we are on the wrong path. The last one, the biggest thing on top is this n squared. Biggest thing on bottom is that n to the 4th. And then in this case, it reduces to 3 over n squared. And now we finally have a P series where the exponent is big enough, more than 1, P is 2. And that's going to make this whole series converge. So this one would have been choice E. So how do we do on that, by the way? Did we do all right? I hope, maybe. We'll find out. So I want to look here. It's okay. I was kind of on this slide here earlier, and I wanted to make sure that um, I kind of talk about this before we end. Another series that is pretty important for multiple choice, and it's becoming more and more important, I think, for the AP exam, is this alternating series test. And it's important for two reasons. Number one, it has an important idea behind it. But then number two, remember where all this is leading up to power series, right? Like describing functions as a series and with X involved, right? When X shows up, it's like a power series. And two of the most commonly used power series, you have to know three of them for the exam by heart, right? When you build a Taylor series or a Taylor polynomial, um, that's a power series, by the way. If a power series converges, it's a Taylor series. So if you hear the word power series and Taylor series, they're all the same thing, essentially. Like there's some very small nuances, but nothing that would have impact the BC exam at all. So if you hear the word power series, just think Taylor series. Any power series that converges to a Taylor series. So it's like the same idea. But all those power series and Taylor series, you might have to make some from scratch. You might have to create your own power series based on information. But a lot of them are built from other known series. And so there's three series that you have to know. You don't have to. I guess you could create them from scratch, but they're common enough. They want you to know them so you can use them for other things. Sine of x, cosine of x, and e to the x. Well, sine and cosine are both alternating series, right? They're both alternating. And so that's a very important idea that we learn the alternating series test, because this is what allows us to know that that formula for sine of x works for all numbers. Like it always converges to sine of x. Why? Because no matter what you plug in for x, you get an alternating series that meets these requirements. So the alternating series test is number one, a series is alternating, right? That's the key. What does alternating mean? Alternating means the terms bounce back and forth, right? Like it's not you have a lot of positives and a lot of negatives. It means literally it goes back and forth between the two. I think my cat is going to sneak in here. I got to get my cat down. See, look, little visit of my cat. I have a little kitten. She's very curious, and she loves to enjoy me when I do my webinars. I have to kind of keep her away on the side. But the alternating series, it has to alternate back and forth. So if you think about like a sine function in general, the derivatives go positive, positive, negative, negative, positive, positive, negative, negative. So sometimes when you have some functions, half are positive and half are negative, but it's not technically alternating. So it needs to be alternating back and forth. And what's the dead giveaway? That -1 to the n power is like an alternating like thing. You start seeing that, you're like, oh, it's one of those, right? Or -1 to the n-1, the same idea. The only difference is this just changes whether your first number is positive or whether your first number is negative. But either of those would create an alternating series. And so you're always looking for n. And I think the one kind of not exception, but one thing to also keep in mind once you've gotten a hang of this, look for n, what's the role, between p series, geometric, and ratio test, is look for alternating, right? Add that component to it. So if something's alternating, it kind of should stand out to you, like, oh, wait a minute, it's alternating. That almost trumps everything else in a way, right? It almost like supersedes some other stuff. So a series, going back to the very beginning of today, we said you're adding up an infinite amount of things you're adding to your pile, right? I'm throwing money on a pile, throwing money on a pile forever. And the question we ask is this pile going to get out of control, or is this pile going to stay contained, right? Is it going to get too big, or is it going to have like a, we can keep it, manageable, where there's a limit to it, right? Well, alternating series, you're not just adding, you're adding, but then you're subtracting, and then you're adding and subtracting and adding and subtracting. And so as you can imagine, because we're not just adding all the time nonstop, we're taking some away. And we add some more, take some away. So something alternating then is really going to give us a better opportunity for the series to converge. If something's alternating, it's easier to converge. It's not going to converge automatically, but it's easier because you don't have to just add, right? You're going to take a little bit away. It's like your bank account, right? This is why people aren't trillionaires, right? Because in our bank account, we put money in, like, your paycheck or whatever, but then we spend money and money comes out, and we add money, spend money, add money, spend money, add money, spend money. And so our amount in our account, is manageable. sometimes depressing, sometimes exciting, right? But it's manageable because we're doing both. If you only added, that amount would just kind of get out of control in a kind of a good way, right? It's called like investments, retirement, stock market, possibly like grow, 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 and it gets big, 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 right? So alternating makes it easier to convert. So if you see an alternating series, there's a lot of times a pretty good chance it might converge. So the rules for alternating are a little bit different, right? Number one, in the very beginning, we said for any series to ever converge, the terms you're adding up have to approach 0. That is 100% true always. And the second rule was they have to approach 0 fast enough, right? Quickly. So if a series is alternating, there's two requirements. Number one, the terms that you're adding up have to approach 0. Done. But what's fast enough? Well, it turns out that fast enough is a little bit easier to achieve with alternating series. And the only requirement is the terms are approaching 0 in a way where they just keep getting smaller every time. So they don't go up and down and slowly get closer to 0. It's every single number is smaller than the number before it. They're getting smaller, 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 smaller. And it says at some point. So this fancy talk here where n is greater than n means at some point in time that happens. So maybe the first 10 numbers, the first 3 numbers, the first 50 numbers don't do this. Maybe the first 20 or 50 numbers kind of go up and down, up and down. But at some point, for the rest of the problem, every number gets smaller. As long as that happens and the terms approach 0, the alternating series will converge by the alternating series test. And the nth term test in the very beginning of series, we say, if the terms of a series do not approach 0, the series diverges. And we say if the terms of the series approach 0, then we don't know. That's only half of the requirement, right? We have to also do a test to see if they're approaching 0 fast enough. The alternating series, the idea, since we're alternating, if the terms of the series approach 0, as long as the terms are getting smaller, then there really isn't a fast enough. No matter how they go, it's fast enough. No matter how they're getting smaller, it's fast enough. It doesn't have to go fast. It's just if they're getting smaller, that's fast enough for me. But that only applies because it's alternating, right? The alternating component allows us to do that. So I just have like a really quick, 6 series here on the left. And we're not even really answering whether it converges or not. I'm just going to make it a choice. Like, actually, I guess we will see if it converges. Does it converge by the alternating series test? And then notice in red, I don't say it diverges. Like this is what I think is a little bit tricky about the alternating series test. It's kind of like the nth term test. The nth term test can tell you if something diverges, but the alternate of that is not it converges, right? Like, oh, it diverges. Well, if the nth term test doesn't apply, doesn't work, that doesn't mean that it converges. It just means you don't know. So the nth term test, the only possible answer it could tell you is diverges. If it doesn't tell you it diverges, then you don't know. You have to do a different test. The alternating series test is a series of convergence. It doesn't actually, give us divergence. So it just says if these two things are true, it converges. If these two things are not true, that doesn't mean it diverges. It just means we don't know necessarily. And you might have to use a different test. And so we don't ever say this diverges by the alternating series test. It's just if it meets these requirements, it converges. If it doesn't meet those requirements, it might diverge. It could converge, but it'd be a different test. And so the first one we notice here is this -1 to the n over n squared. Notice this is definitely alternating, the -1 to the n. So once you know it's alternating, the question is, look at the rest of the problem, 1 over n squared, and ask yourself, are those numbers getting smaller and approaching 0? A 1 over n squared certainly is going to keep getting smaller, and it's going to approach 0 because 1 over n squared, as n goes to infinity is 0. This is a really classic example of the alternating series test. Now, if it wasn't alternating, if it was just 1 over n squared, then it would be a p-series, right? Like 1 over n squared is a p-series where p is 2. And we know that a p-series where p is 2 certainly converges. And if something is alternating, it can never make things worse. That's the nice part. If something converges and then you make it alternating, it will still converge. Like alternating will not turn a convergent series into divergent. Alternating can only help. So alternating can take any series, and if it already is convergent, it will still be convergent. It just might converge even faster, right? Uh, but the power of alternating series is sometimes a series is divergent, but the alternating piece of it suddenly allows it to be convergent. So alternating will only help something converge. And so this is a P series without it that converges. Of course, the alternating version will have to converge automatically. But in this problem, you would have to say by the alternating series test. If something's alternating, you can't call it a P series. Why? Because there's multiple n's, right? N is a base on the bottom, but it's an exponent on the top. It's like a kind of a mixture of geometric and P series, but because of the alternating piece, we can go straight to that test. Choice B, right? We see the alternating component there, the -1 to the n+1, that's alternating. So the only question is, are these terms next to it approaching 0? Well, 2n minus 1, 7n plus 3, that is going to approach 2/7, right? Because the n's are going to cancel. That does not approach 0. This right here, the alternating test does not apply. And so it would be incorrect to say this series convert or diverges because of the alternating series test. You can't say that. This series does diverge, by the way, but it diverges by the nth term test, right? Remember the rule number 1, the terms have to approach 0. Well, these terms don't. They don't approach 0 at all. And so that's why it diverges. So it's kind of like, mincing words, like, well, it kind of helped us, but technically the alternating series test, if it does apply, it might still diverge, but it's probably from another test technically. I want to show this choice D for a moment, because one thing you might see sometimes is a kind of a sneaky College Board way of alternating. For alternating, we kind of look for that -1 to the n+1 idea, uh, but it might look a little bit different. Cosine of pi n is kind of a sneaky way of doing alternating. Because if n is 0, well, cosine of 0 is just 1. But if n is 1, you get cosine of pi, which is -1. Then if n is 2, you get cosine of 2 pi, which is back to 1 again. If n is 3, cosine of 3 pi is back to -1. And so this just bounces back and forth between 1 and -1, which makes it alternating. So it doesn't happen very often. If it happened to be multiple choice, but you kind of realize, oh, this is a sneaky alternating problem. And then the n to the -1 means over n. This is the alternating harmonic series, right? It's -1 to the n over n is what it really turns out to be. And that's alternating harmonic. And the terms are getting smaller. 1 over n gets smaller and smaller and smaller. The terms do approach 0. So that is certainly going to meet that requirement. And the last one I want to mention is choice C, because this one looks like it's alternating. Right, -1, you see that -1 to a power, but notice it's not to the n, it's to the 2n. So no matter what you plug in for n, if you plug in 0, you get -1 to the 0, which is 1. Okay, we'll plug in 1, the next number. We'll plug in 1 for n, you get -1 squared, which is still 1. Okay, plug in 2. Okay, well, now I get -1 to the 4th power. Well, that's still 1. So every time you plug a number for n, the terms are still 1. It never actually alternates. It just stays 1, 1, 1, 1, 1. This is not alternating at all. The alternating series test does not apply. Just FYI, this series ends up converging because it's geometric, and you could prove it that way. So the reason why I brought this one up, you won't see this very often on multiple choice, but when you do your Taylor series, like FRQs, like that question 6 in the test that Mark will talk about next weekend, a lot of times on those questions, they'll ask you for the interval of convergence, of a Taylor, of a series, right? A power series, what's the interval of convergence? And you do the ratio test and you get this kind of interval. And then once you do it, we have to check the endpoints because the ratio test is inconclusive, right? It's unknown at the endpoints. And so you plug in the endpoints back into the problem and you check to see what you get. And a lot of times on those endpoints, they turn into like harmonic or a alternating harmonic series. And a lot of times the series itself is already alternating, but when you check the endpoints, it ends up giving you something like, when you simplify it, -1 to the 2n, or something like that. And so when you multiply and plug these endpoints in, sometimes it turns what was an alternating problem in the beginning into this, which is no longer alternating. In which case you guys, oh shoot, that's just not alternating anymore. So it's a pretty important idea to check for those, and you'll see more about that next week. So that kind of gives us some good examples of what that looks like. Um, the last thing I just wanted to mention at all is just this idea of we have something called conditional convergence and an absolute convergence. And so, and I can't write, I wish my pen would write. It won't let me write on the screen. I don't know what's going on with this, but conditional versus absolute convergence, it sounds like tricky at first. And if you look at the book, the definition, like how they do it in the book is so like complicated unnecessarily sometimes how they explain things. So, it's like a bunch of like PhD guys, right? That are like writing these books, like being all technical and they're kind of like being fancy and trying to be the smartest person in the room, right? But then in the heart of it, it's actually kind of easy. It's almost like they don't want anyone to know their secret code. But when we are going into conditional convergence, when we have this harmonic series, for example, I'm going to bring it up here. I'm going to write on it. But we have this harmonic series. And again, I'm using my mouse, so you have to not make fun of my handwriting here, but I'm using a little bit of bad notation, but 1 over n, for example, like that. And then I'm going to bring another p series in, 1 over n squared, like this. And so, oh, that's even worse. So 1 over n squared. Well, I know the one on the left, the 1 over n, that is harmonic. It's a p series or p is 1. And this diverges, right? This certainly diverges. Well, 1 over n squared, this is also a p series or p is 2. And because p is 2, this series converges. No big deal. We did that already. Well, what if I did the alternating versions of each of those, right? So what if I had on the left the -1 to the n over n? That's the alternating harmonic. And by the way, if you ever notice, like on a test, and this happens a lot with uh, interval of convergence with Taylor series, like the question 6 on the FRQ that Mark will finish tomorrow. When you check the endpoints, what shows up a lot of the time is the harmonic series and the alternating harmonic series. And you might have to use the limit comparison test. It might be like 1 over n plus 2, right? So you're ignoring like the little addition part. So you can just immediately just say that this is the limit comparison to the harmonic. But what happens is if something's harmonic or alternating harmonic, you can just say the name of that. Harmonic, it diverges. Alternating harmonic, it converges. So the -1 to the n over n is the alternating version, and that converges, right? It's a convergent series because the alternating series test. The terms approach 0, they get smaller, boom, done. -1 to the n over n squared also converges because it's alternating. The terms are approaching 0 and they're getting smaller, boom, it converges even faster, right? So what happened was both of these alternating series, right, that we had on the bottom in red, both of those series converged. But the question becomes, well, what if it wasn't alternating, right? What if it wasn't alternating, which we see above in black? Above, the 1 over n squared, even if it wasn't alternating, still converged, right? We said that alternating things allow things to converge fast. They allow things to converge quickly, right? It allows things to converge easier, right? Things are easier to converge if they're alternating. So the 1 over n squared one, the -1 to the n over n squared, that converged. But even if it wasn't alternating, it still would have converged, right? We didn't need the alternating. That little -1 to the n really did not impact anything about converging or not. It didn't put it over the top. But the 1 over n problem, uh, did diverged, right? But all of a sudden, by by throwing on an alternating piece on top, it turned that divergent series into a convergent series. So that -1 to the n, the alternating part, was pretty dang important. Like it plays an important role because without it, the series diverges. With it, it converges. This alternating piece is really important because it's what pushed it over the edge into this world of convergence, right? So the idea is if the alternating part does not like play a role, meaning even if it was not alternating, it would still be convergent, like this 1 over n squared. We call that absolute convergent. It's absolutely convergent, meaning if I took the absolute value of it, meaning it was no longer alternating, it would still converge. And then on the left, we would call that conditional convergence, that this one in red converges, right? We said it converges, but it's conditional. Why is it conditional? Because it only converged on the condition that it was alternating. So when you start seeing phrases like absolute versus conditional convergence, what they're asking is, number one, it's not even a question you could ever see unless it was alternating. It's not a question that applies to any series unless it's alternating. So it might ask you something like, is this series conditionally convergent? Or which of the following series are conditionally convergent? Or is this conditional or alternating or absolutely convergent? And the first step is, number one, double check to see if it even converges, right? You got to use the alternating series test. Does the series converge? And if it does, ask yourself, well, if it wasn't alternating, if I wrote it without that -1 to the end, would it still converge? Like, did it need it? And if it needed it, then that's conditional. If it would have converged anyway, that's absolutely. So that's the idea. And that's like a newer topic. They added that to the curriculum like 3 years ago for Calc BC. It wasn't, I mean, you saw alternating series before then, but they never would ask you directly about conditional versus absolute convergence. So we've only seen it on like 2 years exams, because last year, obviously, we didn't get multiple choice due to the online testing format. But one thing I've noticed is when they add something new to the curriculum for AP, they like to make sure they have it on the test for the first several years to make sure everyone understands that it's on the test and you should prepare for it. And so I would not be surprised at all if you see at least one multiple choice question involving this, as well as one part of an FRQ asking, does this series converge absolutely, conditionally, or does it diverge? So they like to make sure those new ideas, those things they just added, are stressed on the exams. And they like to put on both, because teachers, we don't see the multiple choice, right? We don't get to see the multiple choice questions, but we do see the free response questions. So they certainly like to put something new on the free response so everyone sees it and takes notice. Like, oh, they're asking questions about this. I didn't know it was tested. And they want to make sure everyone knows it's tested now. So make sure you're okay with those ideas and checking between the three ideas: conditional convergence, absolute convergence, and just divergence. First question is, does it even converge at all? You could be alternating and diverge, like -1 to the n times n. That just diverges because the terms don't approach zero. But some of them converge because of the -1 alternating, and some of them converge regardless. There we go. Wow, 2 hours of that, of me talking. Man, I wish we were face to face. I hope that when things get back to normal, quote, in the future, I get to do a study session where I can go to Kentucky and see you guys. We can do all kinds of activities and we can interact and have some fun and get those things done. So I hope you learned something today. I hope that my beginning slide that I kind of started off with, I'll go back to here, this convergence made easy. I hope that you feel like that kind of happened. Like we were able to break some things down. Of course, there's some smaller details, but things like the integral test and some other tests are really so uncommon that you really, if you don't know those, if you can focus on the ones we talked about today, you're going to be crushing the test. This is like what's most stuff is about. Master these first. If you've got these under control, then start looking at some other ones. Michael?
Thank you, Brian. I've got one more slide to show before I let everyone leave, so I want to share.
Perfect.
All right, thank you again, Brian. That was awesome. I've taught for years and years and years, and I learned something new, and I think that always is the best compliment to give another teacher. So excellent job. The students and teachers today were very lucky to have you do that. I want to say to everyone who joined us, thank you. Again, I'm with Advanced Kentucky. You can find us at advancedkentucky.com. I'm Michael Marshall. Aaron Timmons is my counterpart, who works with the college readiness program that puts on these study sessions. And Bryan Passwater at Speedway High School has his email listed there, and you can use that bit.ly to get the handouts. And as we mentioned earlier, next weekend, May 1st, series with Mark. And I think that'll be a great, great session.
Great. Good luck to you guys on the exam. Let me know how it goes. If you have any questions, my email is, I'll be happy to help you guys out.
Thank you all. Have a great day.
Thanks for having me. Good to see you, Michael.
You too.